In this video, you will learn how to check the linearly independent solution for the second order ODE. In this example, we have second order linear ODE where the coefficients are constant and the right hand side is equal to 0. Therefore, we can say this is homogeneous ODE. So from this ODE, you are going to find the y with respect to x. So this is your solution. And the solution is provided here. Since this is homogeneous ODE, you know that the solution is called the complementary solution. You can see that the complementary solution is composed of two solutions. So your first solution is exponential 3x. Second solution is exponential x. And the total solution is equal to the summation of it, where the C1 and C2 are arbitrary constant. How can we verify this solution? Which one is the actual solution for this ODE? Let's start with the first solution. So we take the differentiation of it to obtain the y prime. So you multiply the coefficient 3 in front to obtain 3e 3x. And then you continue to differentiate again to obtain y double prime, where 3 multiplied 3 here, you obtain 9. Therefore, you can substitute your y double prime and your y prime inside this equation. So on your left hand side, you have y double prime minus with 4y prime plus 3y, where you substitute all the y prime and y double prime inside this left hand side. So you continue the calculation here. So 9 plus 3, 12, minus with 4 multiplied 3, you get 0. When you compare to the right hand side, which is also equal to 0, since the left hand side is equal to the right hand side, therefore we can conclude that y equal to exponential 3x here is the solution for this ODE. Let's continue to verify the second solution. So we use the same step. Take the differentiation of the y equal to exponential x. You should obtain y prime equal to exponential x. Remain. If you continue to differentiate this, you obtain y double prime, which is equal to exponential x also. So substitute the y prime, y double prime into the left hand side here. Then you can obtain your y double prime equal to exponential x. Minus with 4 and your y prime is equal to exponential x. Lastly, you need to add with 3y to substitute inside. Your y is exponential x. So from here you have 1 minus 4 plus 3, where you get your left hand side equal to 0. When you compare to the right hand side, you found that the left hand side is equal to right hand side. Therefore, we can say the y equal to exponential x is the solution to this ODE. In this example, we have success to verify the y1, y2 here are the solution to this second order linear homogeneous ODE. We can combine these two solutions to obtain the total complementary solution for the homogeneous ODE here. So this can be done by using this linearity principle or the principle of superposition. This principle says that if you obtain two solutions y1 and y2 for the second order homogeneous linear ODE, so in this case, the total solution for the complementary solution can be in this linear combination, where you have the first solution multiplied with the arbitrary constant 1 plus the second solution multiplied with the second arbitrary constant. In general, if you solve first order linear homogeneous ODE, then you should obtain one solution. If you solve the second order linear homogeneous ODE, you will obtain two solutions like this case. And once you obtain two solutions, you can obtain the total complementary solution by taking the linear combination of y1 multiplied with c1 plus the c2 multiplied with y2. So when you substitute your y1 and y2 inside, then you should obtain the final complementary solution for the second order. So you can continue this list where you should obtain three solutions for the third order linear homogeneous ODE, 4 solutions for the fourth order, and so on. For example, in this case, you have third order linear homogeneous ODE, and the 3 solutions for this third order ODE are provided here. So from here, how can we obtain the total complementary solution? So this can be done by following the linearity principle here, where you say once you obtain all the solutions for the third order ODE, then the complementary solution will be just in the linear combination form, where you take the constant one multiplied with your first solution plus the second constant multiplied with your second solution. Lastly, you add with the third constant multiplied with your last solution. So you have 3 solutions that is combined in this linear combination format. This gives you the complementary solution. Simple, in this case, you have 2 solutions for this second order linear homogeneous ODE. So based on the linearity principle, we can combine these 2 solutions to obtain the complementary solution using this format. So you can substitute the y1 and y2 inside to obtain the complementary solution. To verify this solution is the true solution for this second order ODE, you can find the y prime and also the y double prime and then substitute inside the left hand side. So after you compute, you should obtain the left hand side equal to your right hand side, which is equal to 0. With that, you obtain the total complementary solution for this second order ODE. Bear in your mind, do not provide the solution in this individual solution format because this is incomplete. You need to combine all the solutions using the principle of superposition here to obtain the complete complementary solution, like this case. So far, we have learned for the second order homogeneous ODE, we have 2 solutions, y1 and y2. And by using the principle of superposition, we can obtain the complete complementary solution using this linear combination format. By doing this, you have success to obtain the complementary solution. Besides that, you must know that this principle of superposition to obtain the complementary solution will be valid if only the y1 and y2, both of them, are linearly independent. So it is very important for us to check if the solution y1 and y2, whether they are linearly independent or not. If y1 and y2 are linearly independent, then yc can be combined in such a linear combination. If y1 and y2 are linearly dependent instead of linearly independent, then for this case, we cannot form this linearly combination. We can use 2 methods to check the linearly dependency of first solution and the second solution. So in this case, your y1 is equal to exponential x and your y2 is equal to exponential 3x. So we want to check whether these 2 solutions are linearly independent or not. So we can use the first method, which is the linear dependency theorem, where you have the c1y1 plus c2y2 equal to 0. You need to figure out what is the value of c1 and c2 to make this equation equal to 0. So if this equation is equal to 0, when the c1, c2 is equal to 0, then we say the y1 and y2 are linearly independent. So for example, in this case, you substitute the y1 and y2 inside. So to make this equation equal to 0, there is only one way to do this. That is to let the c1 and c2 equal to 0. Therefore, this condition meet and we can say that the y1 and y2 here are linearly independent. In this example, you have y1 and y2 equal to this value. Let's try to find whether they are linearly independent or linearly dependent. To check the linear dependency of these 2 solutions, let's form c1y1 where your y1 equal to this, and then plus c2 y2. So now we try to find the value for c1, c2 to make this equation equal to 0. So where you can see it, if we let c1 equal to 1, in this case, then c2 equal to negative 1 over 5. And this will give us 0. So there are a lot of combinations. You can also make it like c1 equal to negative 5 and c2 equal to 1. You will still make this equation equal to 0. Where you see the c1, c2 here is not equal to 0. Where we say c1, c2 equal to 0, only the solution will be linearly independent. So in this case, if it is not equal to 0 for the c1 and c2, then we say the y1 and y2 solution here is linearly dependent. So from here, we prove that y1 and y2 are linearly dependent. When we solve the ODE, we don't want the solution to be linearly dependent. This is not good. If these two solutions are linearly dependent, then you will find the complementary solution into this format. Since the exponential here are the same, therefore we can combine the constant c1 plus the constant 5c2 into new constant c3 here. So you see the complementary solution is only consists of one solution instead of two. So when you have linearly dependent solution, instead of providing two solutions, you only obtain one. So this is not good. For the second order homogeneous ODE like this, you should obtain two solutions, which is linearly independent from each other. Since you only have one solution in this case, therefore there is one missing solution to be found. You will learn how to find the second independent solution later. At the moment, just learn how to check whether two solutions are linearly dependent or linearly independent. So we want the solution to be linearly independent, because by doing this, only you obtain two real solutions to combine the complementary solution. We can use the Wronskian method to check whether solution y1 and solution y2 they are linearly independent or not. So if you form this determinant where you have the y1, y2 here and the differentiation of y1, so this one is your y1 prime and this is your y2 prime. So if the determinant of this gives you not equal to 0, then we say the y1 and y2 are linearly independent. If the answer here gives you equal to 0, then y1 and y2, both of them will be linearly dependent. Let's check the linearly dependency of the two solutions here by using the Wronskian method. So the W here is equal to the determinant of your y1 and y2, and this is your y1 prime. After you differentiate, you should obtain EX also. So this is your y2 prime. So if you differentiate the y2, you should obtain 3e3x here. So you perform the determinant, then you need to multiply these two elements to obtain exponential x multiplied with 3e3x. So the power for the exponential can be combined to obtain 4x here, minus with these two elements. Okay, so you have exponential x multiplied with exponential 3x. So these two exponential can be combined and the power becomes 4x. These two exponential can be subtracted to give you 2e4x. Since this is not equal to 0, therefore we can conclude the y1 and y2 solution here are linearly independent. So if the y1 and y2 are linearly independent, then we can substitute inside the principle of superposition here to obtain the complementary solution. What if the y2 is changed to phi ex here? So in this case, you substitute into the Wronskian formula. You differentiate the y2 to obtain the y2 prime. So you should obtain same phi ex here. So perform the determinant. So multiply between these two, you should obtain phi e2x minus with the 1 multiplication between these two elements. Then you obtain phi e2x also. So after you compute the subtraction, you should obtain 0. And if the Wronskian formula here gives you 0, this is linearly dependent, where the y1 and y2, they are linearly dependent, and instead of having two independent solutions, we only have one independent solution, which is the exponential x only. For the second order linear homogeneous ODE, you should obtain two linearly independent solutions. So if you only have one independent solution in this case, so one solution is missing. And later we will learn how to obtain this missing solution for the linear dependent case. In conclusion, for second order linear homogeneous ODE, we can obtain the complementary solution from the linear combination between two linearly independent solutions. And we can check the linearly dependency of two solutions, whether they are linearly independent or linearly dependent, by using these two approaches. You can use any of these two methods to check it.